Okay, so folks, welcome to the graphics programming virtual meetup. We follow the Berlin Code of Conduct. We have a Discord server that you can join. If you don't know the link, I can just ask in the and I can put it in the chat afterward. We also have a Twitter account that you can follow. We have a YouTube channel where we put all of the past recordings on it. Today's topic is James Kajiya's famous paper, the rendering equation, which of course introduced the rendering equation. So what is rendering equation? It's this kind of, you can say it's a function where we want to calculate the intensity of light. In the Kajiya's form, we calculate the intensity of light passing from x prime to x, so it's 2 points. And then we have a bunch of terms to calculate the intensity of light passing. So I will split the equation term by term and then just explain each terms. So I means the intensity of light passing from two arbitrary points. That doesn't seem very important since it's just two arbitrary points. But if the x is a surface, then suddenly this I have much more meanings, because we are seeing the intensity of light passing from x prime to a surface. And if the x is an observer like our eye or a camera, then suddenly the problem even gets more interesting, because that's exactly what we want to calculate in rendering. So to calculate I, Kajiya kind of separates the equation into a bunch of terms. G is a geometry term, which says if the path between the 2 points is not occluded, we have this quadratic force rule where 1 divided by r squared, and r is just the distance between those 2 points. If something occludes those 2 points, the path between those 2 points, we just get 0, which means the whole rendering equation will be 0 between those 2 points. Then inside this gent sum, we first have the emission term. So of course, if x prime is not a light source, then we just have 0. But if x prime is a light source, then we have a certain emission term from x prime to x. And the energy contribution of the emission term, if it is not occluded, and if it is a light source, is just we times the geometry term times the emission term, and then the emission term is per unit time, and then it is also per surface area of the source point and per surface area of the destination point. So that's why if we want to calculate the actual energy, we need to integrate back all those terms. Then there's this surface integral, where we just need to calculate the hemisphere around this intersection, this x prime, to get, in this case, it's a hemisphere. If it's a like transparent surface, then we need the whole sphere. We basically need to integrate this whole surface to get all the incoming light contribution from the surface to this point and how they contribute back into X. So first, notice we introduced a new point called X double prime, because we need to use this X double prime point to represent a point on the surface integral. And then we have this most interesting scattering term, which in modern terminology is kind of just our BSDF, even though this scattering term is a little bit different from BSDF, where it represents this scattering term represents a 3-point unoccluded light intensity. And also the random equation is recursive. So this scattering term is just a function that it doesn't consider how much actual light intensity passed from X double prime to X prime. So we need to add another term to actually calculate the light transportation from X double prime to X prime, and that's exactly our random equation. So we just call it recursively. And similarly, if we want to calculate the energy contribution for the scattering term, if it's not occluded, then similarly, then we do similar stuff. And if we want to calculate the energy, we need to integrate back with the time, also the surface area of all the 3 surfaces. Then the Kajiya paper start to talk about the relationship between his random equation and the more traditional terms in terms of radiometry, but instead I think I will talk about, because it's just a bunch of boring algebraic manipulations, so I don't think it will be very digestible on the slide. So instead I will talk about the random equation in terms of direction, which is not in the paper, but it's introduced in another paper in the same year that can be considered independently contributed to the discovery of random equation. Where this form is maybe more familiar to most of the people nowadays, where when we see random equation, we will see a point and a direction vector instead of another point. So an interesting thing about this representation is, first, we don't have a geometry term anymore. The geometry term is completely implicit in this representation. Since we are calculating direction, so we don't need to calculate the occlusion between 2 points. And everything else is almost the same. We also have this cosine term, which in the Kajiya representation is really just inside the scattering term, but in this representation, we usually have an explicit cosine term or a dot product term to kind of represent a Lambertian law, where just the instance angle of light to the surface will contribute to how much the final light contribute. You may see something different in this form because everyone writes random equations slightly differently. For example, in some sources, you may see an error in this BRDF, or in some sources you may see more parameters, but the general idea is the same. The random equations in this form does have limitations. I will talk about some of them. First, random equation is essentially a geometric optics optimization. We just consider those 2 points, we draw a line between them. So in this random equation, we still consider light as ray. But in reality, if you know a little bit of modern physics, then you know this thing called particle wave dualism, and we really need to get into this level of particle and waves if we want to model certain light phenomena. For example, wave diffraction, which happen where we have a really small narrow gap and a huge obstacle and narrow gap. If this narrow gap is almost as small as the wavelength, then we get this interesting effect of the wave just get, when we have wave pass through and then we have wave scattered into all the directions. And this is one of the effects we can see in the light in the real world, but can't be represented in the random equation. Another effect we see is interference. So if we have 2 sources of waves, we can have in some place, we have constructive interference where those 2 waves just add together. And in some place, we have destructive interference where those 2 waves cancel each other, and thus we can get some really interesting phenomena, but random equation can't model that because we model light as rays. Another thing the random equation can't do is that light can't exit the surface at different points. So notice the scattering term here, we have 3 points. We don't have a 4th point. So this basically, that's why we call it BSDF. It's just bidirectional surface reflection. We don't consider the possibility of light enter the surface and then just scattering inside the surface and then come out from a different point. So we can't do subsurface scattering with this representation. Now, then Kajiya start to talk about method for approximate the random equation, because we just have this equation, it's a bunch of math. It is completely useless if it can't translate into any practical stuff. But first, let's talk about some theories. If you are not familiar with Neumann series, it is a generalization of the geometry series. But instead of using a constant, the Neumann series use an operator. First, we have this random equation. Even though we start to use this m, which is not actually a constant but an operator that's used to represent the whole surface integral stuff. We do some algebraic manipulation. Basically, we just move the GMI term to the left-hand side. And we can then divide this term to the right-hand side. Then certainly this form should look familiar, of 1 divided by 1 minus something. if you're familiar with, still remember the geometry series from either high school or like calculus class in college, then you know, if 1 minus gm is less than 1, which is always satisfied in our random equation, we can expand it into different terms. So we have this zeroth order term, first order term, second order term, third order term, etc., etc. We can also write it in this summation notation. But the interesting thing about this Neumann series is this series actually have meanings in each terms. Now, in case if you want to think about in retracing, this is 0 bounds. This is just light source directly come to the eye. So that's why we only have emission. This is 1 bounce. And this term is 2 bounds, 3 bounds, etc., etc. That is pretty interesting. But how can we apply that to practice? The first totally ad hoc approximation with our rasterization pipeline is what Kajiya called Utah approximation, because it's developed by the researchers at the University of Utah. We only consider the first 2 terms in the Neumann series, except in the second term. In the second term, we really need to simplify the lighting without we can't do any kind of surface lighting. Instead, we only can do point light. And the Utah approximation start very easy. This is early image that the researcher at the University of Utah can produce. And this is what our rasterization pipeline can do. It can produce pretty good images, but with a lot of extensions to the original algorithm. So the so-called Utah approximation, first, it's ignore all the scattering effects except the first. The geometry term was really hard to compute. Even in Kajiya's time, it was still hard to compute. But the good news, we only need to calculate the G term with the final scattering toward the eye. If we don't consider interesting effects like shadows. And we all know nowadays it's not hard to compute anymore. We just use the buffer and end of the problem. But at that time, it was not that easy. No extended light surfaces were allowed in the Utah approximation. As a result, light computation become a small sum rather than a surface integral. So if you have done OpenGL, kind of basic OpenGL programming or like any kind of graphics programming before, then this kind of sum, a bunch of point light may seem familiar. And but we can add extension to that to allow actually surface light. Over time, many extension to the rasterization happens. We now have shadows, we have area lights, we have transparency. We even have screen space effects to mimic what is missing of the higher order term in the Utah approximation. Now come to the 1980s, when Whitted introduced the retracing approximation. Of course, Whitted doesn't call it that. It's just a retracing algorithm with that Whitted paper don't have that much math at all. But the idea is it still can be considered the random equation. But with this approximation, The only difference is this M term is not the real M in the Neumann series, but it is itself an approximation that it is a sum of two terms from the reflection term and the refraction term. But otherwise, we have this infinite series kind of just approximated, and we can get some pretty good results in 1980s. The next iteration is so-called distributed retracing approximation, which basically use some Monte Carlo method when calculating light sources. So we can, so unlike the weighted retracing, we can actually do some area light, and we have some cool effects like soft shadows. But we still haven't used the Monte Carlo method to describe things like each individual pixels yet. Now there is a radiosity approximation, which also got introduced in 1984. Radiosity is kind of tricky because it can only handle energy balance for perfectly diffuse surface. So we can see that this BRDF with no angular dependencies, because with all this different angle as input, we just get constant. The radiosity of a surface element at our intersection point is just an energy flux of the total hemisphere. Unfortunately, this derivation have a bunch of terms, use a bunch of terms from the slides I decided to delete. So, but this theta prime term is, the theta is the incident angle of the ray at the intersection point, and this I is radiometry intensity. And we just do a bunch of manipulation. Then we get a result. The so-called radiosity is the energy flux of the total hemisphere, and we can tie it back into our previous rendering equation. We can then substitute the rendering equation in. And if there is occlusion, then the contribution of the emission term is 0. Otherwise, the contribution of the emission term is a constant times the surface area of the intersection point. And similar for contribution for the reflectance term, where H is the hemisphere incident energy per unit time per unit area. We don't need to really understand this stuff, but the cool thing is, combine the previous two equations, we get this equation, which is exactly what the radiometry folks proposed in 1984. So radiosity is also tied back into the rendering equation. So that's pretty cool. But then Kajiya introduced a new algorithm. He himself called it using Markov chain to solve the random equation, but nowadays we just call it path tracing, where we first choose the point x prime in the scene visible through the image aperture to a select pixel x on the virtual screen. Yeah, sorry, is there a question? Is there a question, or like I need to mute someone? Okay, I will just mute you all and I will just mute you all. If you want to talk, you can just then you unmute again. And then we add the result to the Reddit intensity. But for the length of the, and then for the length of Markov path, we need to do is select another point x double prime and then calculate the geometry factor. Then if the geometry factor is not 0, then we calculate the reflectance function and then multiply by the, I think this is a typo of the original paper. It should be, this should be the, this should be the original random equation I, but they say it's the, I don't know why they get this epsilon term here, but if I'm wrong, someone can correct me. Then we just add this contribution to the pixel intensity. So compared to Radiosity, path tracing actually perform a powerful importance sampling optimization, even though we don't usually think this way. So if the geometry factor is 0, which means the point is occluded, then we know the contribution is 0, and then we don't need to continue to calculate the reflectance function. This is actually importance sampling, because in the importance sampling we also have this, if the contribution is low, then we just send less points to it. If this point is more interesting, we send more points to it. Then in this case, if the point is totally not interesting, because if it is occluded, then we just don't send a ray to it at all. So that's a rather interesting. And compared to the previous retracing method, where we send the reflection and refraction rays at each surface, we instead just always send one ray, either reflection or refraction, through by some probability. So we have this one uniform path. Though we still need to calculate the direct light contribution in this path tracing method. The good thing with path tracing is that we can have more interesting effects, but secondly, we don't have this exponential explosion of terms in the weighted retracing. We just have more and more passes with the more depths we go into. Now Kajiya start to talk about some sampling stuff. I also considered removing this part from the slide, but at the end I decided to keep it. First, let's have some review of sampling. For uniform random sampling, we all know it's just what we usually do when we write our first pass tracer. We will do is just uniformly random sample a bunch of points, but it have very high discrepancy, aka we have a lot of clump at some point and also just empty space at some other point. So that's not nice. That's why also there's some more advanced techniques such as blue noise comes from to address this problem with our uniform randomly sampled white noise. But a simple way to help this problem is to use a stratified sampling. So in this case, we just kind of jittered different samples inside each subpixel small grid. And in this way, certainly, voila, we have a much better distribution of our samples. And then Kajiya says, we also want to apply another useful technique called sequential sampling, which means the sample of the integrand are repeatedly collected until the sample variance of the integral estimate fall below a fixed threshold. This is really cool, but it is not compatible with the stratified sampling we mentioned in the last slide, because we can't uniformly subdivide the domain if we don't know precisely how many samples we want to collect. This is the similar kind of problem where if we just let's say we have a random number generated by random bits, then we want to calculate some uniform distribution by a dice roll, so it's 1 to 6, and we just use modular operator on it. Then actually we don't get a fair dice roll because we can't split the whole domain of integers exactly by 6. And this is the same problem we have here, that we don't know how many samples we want. So we can't split them fairly into each individual grid. And so this is not nice. We introduce in some bias if we combine those two techniques. So Kajiya invented this interesting technique called sequential uniform sampling. I don't know if this kind of technique is still used today because it needs to keep expensive tree data structure of variable size grid. So basically you need to keep all your previous samples in a tree. Then when generate a sample, we split the grid, and then the new sample this old sample will be in one side of the subgrid, and the next sample will be generated on the other subgrid. And then we just do this recursively. So here is the algorithm. First, we refine the node. If the node is an internal node, let's say if we want to generate another sample from this graph, if it's an internal node, then we just continue. Choose a subnode with this, choose a subnode subroutine. And after we choose a subnode, we just recursively do that. So in this case, we probably go here, go here, go here. And then we split the leaf node. So we probably split here. And we probably have a split at here. Our S4 will be on the left-hand side of our new subleaf, and then if we want to add a S6, it will be at the other side. And for the true subnode, we basically just calculate the depth of the left-hand side and right-hand side and whether they are balanced or not. This algorithm is 1D, but we can extend it in higher dimension via KD tree, where we just select different axes in term. And then Kajiya also introduced the hierarchical integration on top of the previous sequential sampling strategy, where we compute a Riemann sum using the volume of the cell and the value of the cast sample as integrand. So instead of just calculating the value of each individual point and then treat all their contribution to be exactly the same, we using Riemann sum, and then the contribution of each leaf cell is basically the area or volume. The question is this a photo of an oscilloscope? I don't know. But this is a photo used to demonstrate the convergence of the naive sampling using white noise, and then with all these additions of Kajiya, where they use, and in the Kajiya's approach, we get much better convergence behavior. Here are some results of the Kajiya's paper. For this picture, the left-hand side is image rendered by ray tracing. We have just weighted style ray tracing. We have hot shadows. We have reflection. So pretty cool. But on the right-hand side is what Kajiya used path tracing, and we can see here there are some interesting stuff get missed from this picture and get pick up in this Kajiya's path tracing algorithm. And this is probably the most famous picture in the Kajiya paper, where it's used to demonstrate a bunch of interesting light phenomena using the path tracing, where we have soft shadows, we have this good-looking refraction, we have ambient occlusion. And now I will talk about some further reading materials. I will post the link of all of those afterward. First is another paper, the radiosity method for non-diffuse environment. So this is from a radiosity folk, but they kind of independently discovered the rendering equation in the same year. So this is another paper like classic paper worth reading. And also, this paper introduced the rendering equation actually in a form that used the point and direction form instead of 2 points, which is closer to what we see rendering equation today. We have PBRT. Of course, it talks about rendering equation. We have this work called Advanced Global Illumination. Of course, it also talks about rendering equation. We have this thesis called the Robust Monte Carlo Method for Light Transport Simulation. It also talks about rendering equation, but also on top of path tracing, it introduced a lot of cool stuff, such as metropolitan path tracing. So I haven't read this, and I only read part of the PBRT and Advanced Global Illumination. So this further reading is also a further reading for me too. Yeah. Thank you for coming to the Graphics Programming Virtual Meetup. Any questions before we end the recording?
Something earlier, but do you have any idea or anyone know why we shifted to moving the cos theta term into the rendering equation rather than being in the BRDF? I wonder if there's like a specific reason for that.
Now this is not a BRDF exactly because this. I think I don't know. I'm just learning this stuff myself, so I don't know. But my guess is when this is like more standard radiometry terms, where we can talk about radiometry stuff like radians, etc. But in this representation, Kajiya's formula, it's just all of those terms is defined in that paper, basically.
That's fair. Yeah.
Also, I think get rid of the geometry term is a good thing, because with the path tracing kind of algorithm, this term is kind of implicit. We don't even think about it that much. So I think this formula is better for modern stuff, at least for our typical usage.
I don't know, since it's about direction and vectors, with that cosine theta there seems to be something with projection, just the intuition. I don't know either, but just a guess.
Oh, you mean this cosine?
Right, that was the question, right?
This cosine term is for the Lambertian law. So if the incident angle, like if the incident vector is higher, then we have a higher contribution. If it's lower, then we have lower contribution, basically.
Ah, yeah. So yes, the projection in that direction. That makes sense.
Yeah, exactly. We have this paper mentioned in the chat. If we take a look afterwards, Peter Shirley reads kind of write a lot of papers in this field, probably. Any other questions?
Yeah, I had one. Can you go back to the epsilon, the original ordinary equation? Yeah. What's the definition of that epsilon again? Right. But it has an epsilon in there again. So is that like recursive?
No, this is not the epsilon definition. This is this is the energy contributed by the emission term.
Right. Okay. So what is epsilon then?
So epsilon, you can just think it as unoccluded lighting contribution from x prime to x, but it is per unit time per surface area at each point. It's a little bit weird because it's not using the standard radiometry terms.
So there's I just wanted to see like a definition for it. You know how, because you had definition for G, you had definition for I and the rest of it, P, but I just didn't see a definition, a clear definition for epsilon.
Well, no, it's just like we don't have definition for the scattering term because that depends on the light source or depends on the material, right?
Okay, all right.
Okay, so if there are no questions here, I will end the recording. Okay, so